Let us now discuss about data mining supervised. When it comes to supervised learning, we know that the output variable y is known to us. So in the historical data, if the output variable y is known, then it's called as data mining supervised. And in the historical data, if the output variable y is unknown, it is called as unsupervised learning. These are the 6 techniques that we would be learning as part of data mining supervised learning. Of course, alongside you'll also be learning about ensemble model such as boosting and bagging that would follow after these 6 are discussed. As part of this tutorial, we'll discuss about k nearest neighbor, post which we'll discuss about naive Bayes, decision tree, random forest, support vector machine, and neural network. For now, it's KNN. KNN stands for k nearest neighbor, and when the output variable that you're trying to predict is categorical, you call it as classifier. If the output variable of interest that you're trying to predict is a numerical value, then it's called as prediction or regression technique. Okay, here is an example from KNN, or in this KNN technique. If you choose a value k equal to 1, it is called as 1NN model, 1 nearest neighbor classifier. And here we have multiple numbers. All the ones which are written in different formats, handwritten digits basically, belong to one class. All these 2 which are handwritten, different people write 2 in different way. This is the second class. Third, fourth, fifth, sixth, seventh, eighth, ninth, and all 0 belong to the 10th class. Since we have 10 different classes, the problem that we are dealing with is called as 10 class problem. Now, say there is a number 4. We need to assign this number 4 to one of these classes. And if I ask you on which class would you assign this particular digit to, you would obviously say that you're going to assign this to class 4. Now this is fine, we will further understand this, but what are a few applications pertaining to this kind of number matching? Think about the postal department. When you post something, some person, XYZ person, you might write the address which is handwritten. And when you write the address, you also provide the PIN number. Say you're providing the PIN number as 500438 or whatever be. In most of the developing countries or underdeveloped countries, the postal department people would manually read this and segregate to a specific location area where this particular post has to reach. However, when you look at the developed countries, the postal department that they have is digitized, and they use these kind of algorithms to quickly match 5 to 5, 0 to 0 class, 4 to 4 class, so on and so forth. And they're going to, or your machines would automatically read this post and segregate it and send it to the appropriate location. If you look at 4, a few of them might write like this, a few of them might write like that, a few of them might write like this, and there are multiple ways, right? I've seen people write like this also. So for humans, it's very easy. The moment you look at this, it's easy to understand and say that, hey, this is 4. But for machines to understand, you require some kind of algorithm. Yeah, that is the algorithm that we're going to discuss now, which is KNN, K nearest neighbor. And in most cases, in majority of the developed countries, if say I write a check for $1,450 and give it to you, in developing countries you have to go and submit this particular check to the banker or the bank employee. He would then check the check that you have, he would verify the details, he would verify the signature, and then give you the amount. In contrary, if you look at the developed countries, you can just walk into an ATM scan the check, and withdraw the amount. Now that's very critical. If someone, writes a specific digit which is slightly weird, you should not be, or your algorithm should not classify or misclassify these digits. $1450, it has to be 1450. It should not so happen that, hey, this 4 is read as 8. That's going to be tricky, right? Then you'll be losing $400 straight away, and people will lose faith in ATM machines to be used for scanning your checkbooks. On similar lines, we also have nowadays mobile scanners. You just need to scan the check that you have, and amount would be directly deducted to your account. That is the way world is moving, thanks to these kind of algorithms which have made these kind of business scenarios possible. Let us understand the same thing using a different example. Say you have a two class problem. Say you want to classify an email as spam or not spam. Say all the pink is spam, pink class equal to spam, and say the blue class is not spam. In this scenario, say there is a new email that you have received, right? And say it is plotted on two-dimensional space, since you have only two parameters or two features using which you're deciding on whether an email is spam or not. Whatever be those two features, those two features that I'm speaking about could be the sender IP address and maybe the body of the or subject of the email. Right? Think about those two. And here you're viewing that same thing in two-dimensional space. That aside, just try to understand the intuition first. If there is a new email, should I classify it as spam or not spam? For that, your KNN algorithm uses the concept of nearest neighbor. And since you have k equal to 1, it's one nearest neighbor. So you have to calculate the distance between each data point to this new email. Or new email to all the data points distance is calculated, and you would choose the least distance. And what is the least distance from this data point? It's very closest to this. Hence, this particular new email is classified and assigned pink class. So the new email is assigned pink class. All right. If you go with the 2NN, say you have a data point here. If instead of KNN, if I go with 2NN, two nearest neighbor, then the distance between each data point to this new email is calculated, and the two nearest values or the two smallest values are chosen. And since you have a match here, you have one nearest neighbor data point which says email is spam, another says it is not spam. Okay, one says it is spam, another says it is not spam. Given this context, which class would we assign this new data point to? Now, we will be in a perplexed situation because we have spam and not spam both when it comes to two nearest neighbor. If this is the scenario, then you go with the least distance once again. And the least distance of the new data point is to the pink class. So you'll assign this a pink class, which says this also is a spam. Now, assume that there is a new data point and you're increasing the k value to 3, which is 3NN. In this scenario, if you calculate the distance of all the data points to this new data point, these would be the three nearest data points. Given this context, which class would we assign this? We have to assign this to a blue class because now we have a majority. Two are blue and only one is pink. So going by the majority rule, you're going to assign this blue class which says not spam. All right. In that way, you can keep on increasing the k value. Say there is this new data point. If you go with 1NN, you're going to assign this a pink class. If you go with 2NN, still you're going to assign this a pink class, the new data point. Why would you assign a pink class? Because though when it comes to two nearest neighbor, you have a pink and a blue, pink is closest. On similar lines, you can go with the 3NN also. You're just expanding the scope. 3NN. So when you go with three nearest neighbors, you have two blue and one pink. So you'll assign this new data point blue class because majority is blue. On similar lines, you can go with an 8NN also, 8 nearest neighbor. So you choose the 8 nearest neighbors, and majority of the data points have a pink class. My bad. So you assign this new data point a pink class, and you have only 3 blue, so you'll not assign this new data point a blue class, right? You will rather assign a pink class because the majority is pink. And as in how you keep increasing the k value, the accuracy of the model keeps increasing, but there would be a certain point at which the accuracy decreases. And we need to identify what is that point where the accuracy decreases. And you stop there and decide that that would be the k value. Now let us understand this concept that we have just discussed using a small example, post which we'll look into a real life example and try to solve it using R. So say you have these ingredients 1, 2, 3, 4, 5, 6. You have 6 ingredients, right? And you have sweetness and crunchiness in the food type. Here we have 6 ingredients. Think about these 6 as the 6 emails that you might have received. And all these 6 ingredients that you have sweetness and crunchiness, which are your inputs. These inputs are also called as features, feature 1. And then you have the food type, which is Y output. For each ingredient, given the sweetness and crunchiness, you should be able to assign it to an appropriate class. You should be able to assign it to fruit or protein or vegetable to one of these classes. Since you have 3 classes, it's called as a 3-class problem. This is called as a 3-class problem since you have 3 classes within this food type. Okay, this is the data that we have. Now, if there is a new ingredient altogether, so I'm trying to plot it on a 2-dimensional space, sweetness on the x-axis and crunchiness on the y-axis. If you plot it and try to cluster, you get to see that when it comes to fruits, sweetness is high, and when it comes to proteins, sweetness is less. In that way, you get some information. Now, say there is a new ingredient, tomato. To which class are we going to assign this to? Would you assign this to vegetable or fruit or protein? How do you do that? You need to find out how close is tomato to the other ingredients. And how do you calculate the closeness? Using Euclidean distance. This is a Euclidean distance formula there. So, yep. So let me practically do this and show it to you so that things fall in place. This is the data, right, that we were discussing about. You have the ingredients, you have the sweetness, crunchiness, and the food type. And you have this new ingredient, tomato, which has sweetness as 6 and crunchiness as 4. Now, which class would we assign this to? Would you assign this to fruit, vegetable, or protein? In order to find out that, we need to find out the distance between the new ingredient and the existing ingredient. For example, you need to find out the distance between tomato and apple. How do you find out the distance between tomato and apple? Using Euclidean distance, which is nothing but y2 minus y1 whole square plus x2 minus x1 whole square. There's nothing but square root. 10 minus 6 whole square, 10 minus 6 whole square, 9 minus 4 whole square, which is nothing but square root of 4 square plus 5 square, which is nothing but square root of 16 plus 25, which is square root of 41, which is equal to 6.4, and that is the value which is given here. In that way, you need to calculate the distance between tomato and lady's finger also, which will be square root of 1 minus 6 whole square plus 4 minus 4 whole square. That's square root of 25, which will be 5. So in that way, distance between tomato and all the other ingredients is calculated, and we have the distance values here. And if you go with the logic of k equal to 1, you need to find out one nearest neighbor, which is the least distance, the smallest distance. And here, the least value even given in this particular data set or in this distance matrix or table is 5. And what is a food type corresponding to this? Vegetable. So you'll assign tomato vegetable class. Now let us increase k value to 3 NN. You need to find out 3 smallest values. So in this distance table, First smallest value is this, next smallest value is this one, and the third smallest value is this. So this is assigned vegetable class, this is also assigned vegetable, and this is assigned protein class. So you have two instances where it says that it is vegetable class. You have two instances basically. And there is one instance which says that it is protein. You go with the majority rule. Majority is vegetable, so you're going to assign tomato to vegetable class. On similar lines, if you do it 2NN, you need to find out two values which are very close. And these are those two values. One is here, another is here. Yeah. One is assigned vegetable class, another is saying that tomato has to be assigned to protein class. But we would ultimately assign it to vegetable because whenever there is a match in this way, you will choose the least value of the two. And the least value of the two is 5, which has a corresponding vegetable class. So you'll assign tomato a vegetable class. This is an intuition on how KNN works. It's a very simple yet very powerful algorithm. So now let me take a real life case study and try to explain you all on how it works. So here is the data set, and we have how many entries? In total, we have 569 entries. Let me select count. So we have 569 records or observations. And the output variable of interest here is, this column B, which is diagnosis. Column A has the application ID or the customer ID, right? So this has absolutely no problem basically. I mean, this has absolutely no influence in predicting the output, since these are all IDs, customer ID, that really doesn't matter. And here the output variable of interest is this variable diagnosis. So we should be in a position to diagnose, and given all these inputs, classify on whether the tumor that we are dealing with is benign or malignant. These are all the various inputs that you have, right? So X8, X9, X10 in that way. So radius, mean, texture, perimeter, area, smoothness, compactness, concativity, so on and so forth. You have all these inputs. These inputs are also called as features. Feature 1, feature 2, feature 3. All these features put together is called as feature set. So given the feature set, you should be able to predict on whether the tumor that is being analyzed is benign or malignant. What is this benign? Benign tumor is that tumor which is non-cancerous. It will not spread to the other organs of your body. And malignant is an area of concern. Malignant tumors grow out of control, and that's dangerous basically. That's cancerous. Cancerous is something that's going to grow beyond control. Now this is the data set. Now what we are going to do is we are going to read this data set into R and try to work upon this. Since that data set is in CSV format, we try to import the data set, and here I have the data set which is in CSV format. Only if a file is in CSV format, it will be easier for you to import the data set. If it's in Excel format or some other format, then you need to write the function to read that particular file. Here we have KNN. I'm going to just change this to WBC. Just I'm changing the name, that's it, because everywhere in the code I have that, so I'm changing that. All right. So we have read this particular data set. This data set has 569 observations, which are nothing but rows. These are observations anyways, you know that. These are also called as records, and you have 32 variables which are also called as columns. Yep, columns or variables mean the same. Now, when we have imported the data set using this drop down, this particular function got triggered, read.csv, and within double quotes there is location of that particular file and knn.csv, right? This is in CSV format. And using this assignment operator, you're assigning the output to an object called WBCD. And alongside there is another function that got triggered, which is view. V is in caps. Remember, R is case sensitive. And view of WBCD would show you the data set here in the script window. We anyways know that this ID that you have is application ID or the customer ID, which really doesn't influence on whether you have tumor or not. Until and unless we are very superstitious and assume that anything which ends with, you know, odd number, you might have, a cancerous tumor and all that. Until unless you have such superstitious beliefs, the ID numbers really doesn't matter on whether you have tumor or not. Okay, so we are going to delete that. So I'm going to delete this first column from WBCD. So if you look at this code, this function, WBCD -1. So I want to get rid of the first column and I'm going to assign the output to WBCD. So let me run that. Now we have 32 variables. Let me see what happens if I run this. There we go. This got reduced from 32 to 31 variables. And if you look at WBCD, the first column, which is irrelevant, is gotten rid of. Now, if you want to refer to any of these column names, you have to provide a dollar sign. So it's WBCD dollar diagnosis, WBCD dollar radius underscore mean. So if you want to refer to diagnosis, it is WBCD dollar diagnosis, right? So I'm going to refer to only this column which has benign and malignant entries. Now, if you do a table of that, table of WBCD dollar diagnosis, it is going to just tell you on how many entries in this column are benign and how many entries are malignant. So let me run this. There we go. So in the given data set that we are dealing with, we have 357 benign entries and 212 malignant entries. Now, any of the columns, right, if it takes limited entries, for example, you have diagnosis, it would take limited number of entries, that is B and M, only two are the only two levels. Since these are the only two levels that you have, B and M, this is called as a factor. Any variable which takes a limited number of entries is called as a factor. So here diagnosis is a factor with two levels, which are B and M. If you look at gender, gender is also a factor with two levels, male and female. In this way, if you have limited values which a variable can take, then it's called as factor. All right. So here, this diagnosis column is a factor which takes only two values. Can I say that radius underscore mean is a factor? No, because radius can absolutely take any value. It can take infinitely many values. I'm saying that WBCD dollar diagnosis is a factor which has two levels, which is B and M, benign and malignant. Right. Now, since B and M is slightly misleading, we want to have the complete name as benign and malignant. So I'm saying that WBCD dollar diagnosis, which is factor, has two levels B and M. Change those to benign and malignant. I want a label for that. Label is the name, right? All right, so let me run this. And we have assigned this to WBCD dollar diagnosis. WBCD is this data set. Dollar diagnosis is this. And if you see here, we have successfully changed the B and M to benign and malignant. You know for a fact that table of WBCD dollar diagnosis, this part would provide you these values only. That's the same thing, table WBCD dollar diagnosis. You can also run it. You can select part of the code and run that. All right. Now if I do proportion.table, it is just going to give you the proportion. So it will give you what proportion of entries are benign and what proportion of entries are malignant. There we go. Roughly 62.7% are benign entries. 37.2 entries in the dataset are malignant. You can multiply this with 100. If you multiply these values with 100, if you multiply this with 100, you'll get 62.7. If you multiply this with 100, you'll get 37.2. And if you want all the digits, it'll be 74165. And here it will be 5835. Okay. Now, you want the proportion and you want to round it off to a single digit. If you do that, it'll be 62.7 and 37.2. Let me run this then. There we go, right? And as you already know, if you do summary of something, summary, it would give you mean, median, first quartile, third quartile, so on and so forth. So let me do a summary now on WBCD. And do I want to know the summary of each and every variable? No, I've randomly chosen only 3 variables. Radius underscore mean, area underscore mean, smoothness underscore mean. These are the only 3 entries that, or 3 variables that are chosen here. And if you do WBCD, and if you want to refer to only these 3, you refer that using the C. C is used when you want to refer to specific entries, right? So you're referring to only these 3, and you want a summary of these 3. If you run that, there we go. For radius, area, and smoothness, we have the minimum value, maximum value, the first quartile, third quartile, mean, median, so on and so forth. The reason why we are looking at these 3 is because if you see radius, that has a different scale. Scale here is, or the range is 6.9 to 28.1, the minimum and maximum value. And the range for area underscore mean is 143.5 to 2501.2. And for this, the range is from 0.05263 to 0.16340. Clearly, there is a huge difference in the scale values. There's a huge difference in the scale values, right? 1 digit, 3 digits, there are no digits. It's directly starting from the decimal values. If you have these kind of huge scale difference, then the output that you want to predict, right, would be slightly biased, because since area underscore mean, this variable has a bigger scale value, this will have more influence on your output as opposed to smoothness underscore mean, which is in decimals, right? It's starting from the decimal position there. Hence, we need to standardize or normalize. How do we standardize or normalize? One way of standardizing or normalizing is using z value. Z is equal to x minus mu by sigma. Or you can use another formula for standardizing or normalizing, which is nothing but x minus minimum value of x divided by range. Now, the only difference is if you standardize using this formula, there are multiple ways, multiple other ways of standardizing. But if you standardize or normalize using this formula, the values that you get will be in the range of 0 to 1. This is especially used when you have dummy variables. When you introduce dummy variables, since dummy variables are within this range of 0 to 1, we use this function, especially when you have this kind of data, or when you introduce a dummy variable. All right. This theoretically can range from minus infinity to plus infinity. Practically, it ranges from minus 3.4 to plus 3.4, practically. So I'm writing this custom function. I'm writing a function which would return x minus minimum by range. Range is given using maximum value minus minimum value. And I've assigned this function to an object called normalize. If we normalize these values, 1, 2, 3, 4, and 5, if I normalize this, I should get values which will be in the range of 0 to 1. Let us see. Yeah, it's in the range of 0 to 1. Now, if I normalize 2 digits, if I normalize 1 digit, I got the range 0 to 1. If I normalize 2 digits, still it should be in the range of 0 to 1. Let us run this. There we go. It's in the range of 0 to 1. So when you apply this function of x minus minimum by range, No matter what the data is, it would range from 0 to 1. And I'm applying this particular normalize function on all the columns from 2 until 31, the last column, except for this first column, because you cannot normalize this. How would you find out what is a maximum value? How would you calculate the minimum value? How would you subtract those, right? All those are not possible when you have categorical data. Hence, we are applying that particular normalize function on WBCD dataset, and we want the columns from 2 to 31. And we want the resultant to be a data frame. And we are assigning it to an object called WBCD underscore n.